Session 6, Experimental Designs. Introduction. The purpose of experimental design is to minimize extraneous or uncontrolled variation, thereby increasing the likelihood that an experiment will produce valid, consistent results. Volumes of books have been written about experimental designs. Here, we shall examine some common techniques used to improve the design of experiments. Learning outcomes. When you have studied this session, you should be able to 1. Outline the basic steps in experimental design. 2. Point out the merits of different designs to the experiment. 3. Present ways of control in an experiment. And 4. Indicate ways of minimizing errors in an experiment. Basic steps to experimental design. One of the first design decisions an experimenter must take is how to assign subjects to the various levels of independent variables. The two main possibilities are to assign only some subjects to each level or to assign each subject to every level. The first possibility is called a between subject design and the second a within subject design. The difference can be shown with a simple example. 30 students in introductory psychology have signed up for an experiment that you are conducting to test ability to remember nonsense words. Your independent variable is the number of times you say each item, 1 time or 5 times. You expect that an item presented 5 times will be learned better than an item presented only once. The between subject design calls for you to divide your subjects in half, that is, into 2 groups of 15 students each, with one group receiving 5 repetitions and the other 1 repetition. In bracket, how to select which subject to put in each group is discussed shortly. The within subject design has all 30 subjects learning with both levels of the independent variable. That is, each is tested with 1 repetition and again with 5 repetitions. In brackets, how to determine the order when each subject gets these 2 treatments is also discussed later. Which design should you use? Forms of experimental design. Between subject designs. The between subjects in bracket 2 group design is conservative. There is no chance that one treatment will continue to contaminate the other because each person receives only 1 treatment, in brackets 1 repetition or 5 repetitions, but not both. One drawback, however, is that the between subject design must deal with differences among people, and this decreases its efficiency, that is, its ability to detect real differences between 1 and 5 repetitions of the memory items. In any between subject design, the experimenter must try to minimize differences among the subjects in the 2 or more treatment groups. Clearly, if we took the best 5 memorizers and deliberately placed them in the 1 repetition group and put the worst 5 in the 5 repetition group, we might wind up with no difference in results even, perhaps with the 1 repetition group doing better. To prevent this outcome, the experimenter must ensure that both groups are equivalent at the start of the experiment. Equivalent groups. One way to do this would be to administer a memory test to all 30 subjects before the regular experiment started to obtain a baseline measures of the subject's ability to memorize nonsense words. Subject baseline scores could then be used to form pairs of subjects that have equal or very similar scores. One member of each pair would be randomly assigned to one group and the other member to the second group. This technique is called matching. One difficulty with matching is that an experimenter cannot match subjects on every possible characteristic. Thus, there is always the possibility that the groups, even though matched on some characteristics, differ on some other characteristics that may be relevant. In brackets, matching is discussed in greater detail later in the study session. A more common technique used to ensure that equivalent groups are formed is randomization. Randomization means that each person participating in an experiment has an equal chance of being assigned to any particular group. In our repetition experiment, one way to form two groups by randomization would be to draw names out of a hat, or we could ask each person to step forward and then throw a dice. Even throws would be assigned to one group and odd throws to the other. If we do not have any dice, a table of random members could be used to generate even and odd digits. This method of assigning subjects to experimental conditions has no bias, since it ignores all characteristics of subjects. We expect that the groups so created will be equivalent on any and all relevant dimensions. However, randomization does not guarantee that groups will always be equal. By chance, a greater number of beta memorizers might be assigned to one of the groups. The odds of this occurring can be calculated by the methods of probability theory as applied to statistics. This is one reason why experimental designs and statistics are often treated as the same topic. However, design is concerned with the logic of arranging experiments, whereas statistics deals with calculating odds, probability, and other mathematical quantities. If we are sure that all relevant dimensions have been dealt with, matching is preferable to randomization, but because we seldom are sure, randomization is used more often. Within subject design, many experimental psychologists will prefer the within subjects in bracket one group design, in which all 30 subjects are tested with one repetition and again with 5 repetitions in bracket or vice versa. It is more efficient since each subject is compared with himself or herself. Any differences resulting from 1 versus 5 repetitions cannot be the result of differences between the people in the two groups, as might be the case for the between subjects design. General practice effects. There is a risk, however, in the more efficient within subject design. Imagine that all 30 subjects first learn a large number of items with 5 repetitions and then learn with 1 repetition. By the time subjects begin the 1 repetition treatment, they might have become more proficient in learning nonsense words, or they might be experiencing some boredom or fatigue with the task. Both possibilities are termed general practice effects. These effects are usually assumed to be the same for all treatment conditions, so that it does not matter whether subjects learn with 1 repetition followed by 5 repetitions or 5 followed by 1 repetition. Because general practice effects are the same for all treatment conditions, they can be controlled largely through counterbalancing. With counterbalancing, the experimenter faces the difficulty of determining the order in which treatment should be given to subjects. Again, One solution is to use randomization by drawing the treatment titles out of a hat, using a random number table, or using a computer to order conditions randomly. However, although counterbalancing treatment through randomization produces equivalent orders in the long run, it is less likely to be suitable when there are only a small number of treatments. In most experiments, the number of subjects exceed the number of treatments, so randomization is a good technique for assigning subjects to treatments. Complete counterbalancing makes sure that all possible treatment orders are used. In the repetition experiment, this is easy since there are only two orders, 1 and 5 repetitions, 5 and 1 repetitions. Half the subjects will receive 1 repetition followed by 5 repetitions, and the other half would get the opposite order. As the number of treatments increases, the number of orders becomes large indeed. 3 treatments have 6 different orders. 4 treatments have 24 different orders. 5 treatments have 120 different orders, and so on. As the levels of an independent variable increases, complete counterbalancing soon becomes impractical. Counterbalancing does not eliminate the effects of order. It does allow experimenters to evaluate possible order effects. If such effects are present, and especially if they form interaction with other more important independent variables, steps should be taken to correct this design. The experimenter might decide to repeat the experiment using a between-subject design to avoid order effects. Alternatively, the original experiment could be reanalyzed as a between-subject one by examining behavior in just the initial condition experienced by each subject. Differential carryover effects. Differential carryover effects pose a more serious problem than do general practice effects. In differential carryover effects, the effect of the early part of the experiment on the latter part of the experiment varies, depending on which treatment comes first. Imagine that all 30 subjects first learn items with 5 repetitions and then learn with 1 repetition. As a result of their earlier experience with 5 repetitions, they might decide to repeat to themselves 4 more times the item that is only presented once. This would destroy any differences between the two levels of the independent variable. This is an example of a differential carryover effect, given that the effect of the first treatment on the second treatment differs, depending on which treatment comes first. This is not the case with general practice effects, in which subjects approach the second treatment in the same way, that is, with greater skill, boredom, or fatigue, regardless of the treatment they receive in the first phase of the experiment. Differential carryover effects can be diminished somewhat through counterbalancing, but counterbalancing cannot eliminate these effects entirely. If there is any reason to expect differential carryover effects, we can do one of two things in addition to counterbalancing. We can use the between-subject design or build in a sufficient time delay between the two treatments. Because the between-subject design is less efficient, it will require that many more subjects be tested, but this is preferable to conducting a seriously flawed experiment. If we decide to insert a time delay between the two experiments, we must identify duration of time that is sufficient to eliminate the possibility of differential carryover effects. Small designs. Before turning to a discussion of mixed designs, we would like to mention a variant on the traditional within subject design, the small n design. Small n designs present the levels of the independent variable or treatment to a small number of subjects or a single subject. Because few subjects are tested, a substantial number of observations are recorded for each subject, resulting in a very economical and highly controlled experiment. Small n designs experiments are common in psychophysical, clinical, and operant conditioning research. Just as with the within subject design, the experimenter must be careful to counterbalance treatments and anticipate any problems associated with administering multiple treatments to individual subjects. Mixed designs. Experiments need not to be exclusively be within subject or between subject design. It is often convenient and prudent to have some independent variables treated as between subjects and others as within subject in the same experiment. In brackets, assuming the experiment has more than one independent variable, of course. If one variable, for example, the administration of a drug, seems likely to affect others, it can be made between subject variable. When trials or repeated practice on a task is of interest, it is of necessity to have a within subject variable. Frequently, a mixed design is used, in which some variable is imposed between subjects to see its effects across a second within subject variable. This was the case in the Mattel and Willis 1993 study described earlier. The experimenters designed performance feedback, in bracket, positive versus negative, as a between subject variable based on the expectation that subjects will be reluctant to believe the negative feedback after receiving positive feedback, or vice versa, concerning the group. In contrast, it seemed reasonable for each subject to observe the group engaging in both effective and ineffective behaviors. A within subject variable. This type of compromise design, in brackets, mixed design, is not as efficient or economical as a pure within subject design, but it is often safer. Control conditions. Independent variables must be varied, in bracket, or manipulated by the experimenter. This implies that each and every independent variable must vary either in amount, in bracket, quantitative variation, or in kind, in bracket, qualitative variation, within the experiment. For example, if the amount of regard given to a rat is an independent variable, the amount chosen by the experimenter might be 1 and 4 pellets of food. Alternatively, we could offer different kinds of regard, such as food and water. The technical term for a single treatment or condition of an independent variable is level. We will state that in the first example, the levels of the independent variable are 1 and 4 food pellets, and food and water in the second example. Many experiments contain, in addition to independent variables, some control group, in bracket, between subject design, or control conditions, in bracket, within subject design. In its simplest form, the control group does not receive the levels of interest of the independent variable. In the reward example just described, a control group of rats will receive no reward, or an experimenter might be interested in the effect of noise on studying. Using a between subject design, the experimenter will expose one group of subjects to loud noise for half an hour while they are studying. This is the level of interest of the independent variable. A control group will study the same material for half an hour in a quiet setting, in brackets, a very low level of noise. Then both groups will be tested on the material. Any obtained differences on the test between the two groups would be attributed to the effect of noise. The important characteristics of a control condition is that it provides a baseline against which some variable of interest can be compared. Sometimes, the best baseline is no treatment, but often the best baseline requires some activity. A frequent example occurs in memory research, where a group of subjects is required to learn two different lists of words. The experimenter is interested in how learning the words in one list interfere with learning the words in the other. The experimental group, in brackets, receiving the level of interest of the independent variable, first learns list A, but then list B, and then is tested again on list A. The experimenter would like to show that learning list B interferes with retaining the knowledge of list A. But before any conclusion of this sort can be reached, a comparison control condition is required. Merely comparing the final test of list A with the first test is insufficient because subjects might do worse on the last list. A test simple because subjects might do worse on the last list A test simply because they are tired, or they might do better because they have had extra practice. A control condition with no treatment would have a control group learn list A, then sit around for the time it takes the experimental group to learn list B. Because subjects might practice or rehearse list A while they are sitting around, this will improve their final performance on the last list A test and incorrectly make it appear than in the experimental group. List B interferes more than it really does with list A. A proper baseline condition would occupy the control group during the time the experimental group is learning list B. Perhaps the experimenter would have them do arithmetic or some other busy work that would prevent rehearsal. Sometimes the control condition is contained implicitly within the experiment. Recall the memory experiment discussed earlier, in which the independent variable was the number of repetitions of an item of 5. No experimenter would bother to include a control group or condition with 0 repetitions, since no learning could occur under this odd circumstance. The control condition is implicit, in that 5 repetitions can be compared with 1 and vice versa, since the experimenter might well be as interested in the effects of a single repetition level as a control condition. But it does provide a baseline for comparison, and so for that matter does the 5 repetition condition, since the 1 repetition result can be compared with it. Many types of experiments require more than one baseline. In physiological and drug research, for example, a control for surgical or injection trauma is needed. So a subject might receive a sham operation or the injection of an inert substance, in bracket, a placebo. In the control condition, those would also be compared with other controls that receive no operation or no injection. Errors in experimental designs. It is quite easy to formulate an inadequate experimental design. In this study session, we shall discuss only a small sample of errors in design, ones that are so common, which you should be aware of. Examples include demand characteristics, experimental effects, and automation of experiments. Demand characteristics. Laboratory experiments attempts to capture behavior as it is really influenced by the independent variable. Sometimes, the laboratory setting itself or the knowledge that an experiment is underway may alter patterns of behavior. Many times, research participants spontaneously form hypotheses or assumptions about the experimental's purposes in conducting the experiment and then behave or respond in a way that will satisfy this assumed purpose. Try this simple demonstration to convince yourself that such effects occur. Tell 5 of your friends that you are conducting an experiment for your psychology class and would like their cooperation as subjects. If they agree, ask them to hold 3 ice cubes in their bare hands. Note how many of them hold the ice cubes until they melt. Now ask 5 other friends to hold the ice cubes without mentioning anything about an experiment. Instead of holding the ice cubes until they melt, they will consider your request somewhat strange and soon so inform you. There is something unusual about the ready compliance of those friends who know they are participating in an experiment. Most of them are willing to hold the ice cubes for a longer period of time. Psychologists call the cues available to subjects that allow them to determine the purpose of an experiment or what is expected by the experimenter demand characteristics. To the extent that the behavior of research participants is controlled by demand characteristics instead of by independent variables, experiments are invalid and cannot be generalized beyond the test situation. A well-known example of a demand characteristic is the Hawthorne effect, named after the Western Electric Company plant, where it was first observed. The company was interested in improving workers' morale and productivity. Thus, it conducted several experiments, in brackets, such as improving lighting, to better the workers' environment. No matter what experimental manipulation was tried, workers' productivity improved. The worker knew they were in a special group and therefore tried to do their best at all times. The demand characteristics were more important in determining the workers' productivity than were the experimental manipulations. Experimental effects. A pitfall closely related to demand characteristics is the experimental effect, which influences the outcome accidentally by providing participants with slight cues as to the experimental's expectation. For example, an experimenter might not be aware that he or she nods approvingly when a correct response is given and frowns after errors. The gender, race, and ethnicity of the experimenter are also potential experimental effects. Experimental characteristics are more likely to bias the results of an experiment in research that focuses on issues related to these characteristics. For example, the race of an experimenter who is conducting an experiment concerning the effect of skin color on work performance rating may affect the outcome of the experiment. These effects are not limited to experiments with humans. The experimental effect can also occur in similarly objective experiments with animal subjects. Rosenthal and Ford, 1963, told student experimenters that the rats they were to test in a maze were from special strains either maize brides or maize dough. Actually, the rats came from the same population. Nevertheless, the rats that were labeled maize bride had fewer errors than those labeled maize dough, and this difference was statistically reliable. The student experimenters were observed while they tested the rats. They did not cheat or do anything overt to bias the results. It seems reasonable to state that the lucky students who got supposedly bright rats were more motivated to perform the experiment than those unfortunate ones who had to teach stupid rats to go through the maze. Somehow, this affected the results of the experiment, perhaps because experimenters handled the two groups of rats differently. The best way to eliminate this kind of experimental effect is to hide the experimental condition from the experimenter on the premise that experimenters cannot communicate what they do not know. This procedure is termed a double-blind experiment because the information that could lead to a biased experimental outcome has been deliberately withheld. This procedure was applied to a specific experiment on air pollution, where neither the experimenter nor the research participant knew which subjects or behavioral effects of air pollution. Subject breathed either pure air or air taken from a busy roadway. The air was contained in tanks. The experimenter did not know which tank held pure air and which tank held polluted air. The subject's poorer performance in polluted air could not then be attributed to the experimenter inadvertently disclosing the air quality to subjects or treating them differently. Experimenters' effects are not always this subtle. One of the authors was once involved in an experiment concerning the human eye blink response. Several experimenters helped conduct the same experiment, and it was soon noticed that one of them obtained results that were quite different from those of the rest of us. His subjects started out experimental sessions with massive flurries of frenzied blinking. The cause of this odd behavior was easily discovered. To record eye blinks, the experimenter must attach a tiny metal rod to the subject's eyelid with special tape, ordinarily a painless procedure. However, the experimenter in question had a very heavy thumb and was unable to attach the rod without irritating the eye, causing the strange flurries of blinking, when an experimenter suspects that some aspect of his or her appearance or manner, in brackets, gender, race, or ethnicity, may alter the pattern of subject's behavior. Then, a possible solution is to incorporate these as an additional independent variable or control variable in the experimental design. If an African American experimenter is conducting a research on skin color and work performance rating, he or she could ask a white colleague or research assistant to test half of the subject and then compare the effect of skin color in the two experimenters' race condition. Automation of experiments. Experimental effects can be eliminated or greatly reduced by having computers or other equipment conduct the experiment, so that the subject is untouched by human hands. In many laboratories, a subject enters a testing booth and sees a message on the screen that tells her or him to push a button to begin. Pushing the button causes instruction for the experiment to appear on the screen. The entire experiment is then conducted by a computer. The experimenter appears at the end of the data collection to debrief the participants. giving the aims of the study and explaining how the subject has helped advance science. Until then, the experimenter simply monitors the equipment and the subject to ensure that the subject is following instructions and that nothing untoward happens. Such automation obviously reduces the dangers of experimental biases. Study session summary. In this study session, you learned that experimental designs are concerned with assigning subjects to experimental groups in ways that are expected to minimize extraneous variation. Within subjects and between subjects are two examples of experimental designs. When using the within subject design, the same subject go through all the treatment, while in the between subject design, different group of subjects are exposed to different treatments. The between subject design is safer, but the within subject design is more efficient. In any between subject design, the experimenter must try to minimize differences among the subjects in the two or more treatment groups. This can be achieved by ensuring that the groups are equivalent from the beginning of the experiment, using matching or randomization. You also examine ways to interpret experimental design. End of study session 6. Thank you for listening.